Okay, so I'm going to be giving a series of lectures on statistical aspects of deep learning methodology. So, really viewing, is this really the line where everyone can see? Is it okay for folks at the back to write right down to there? Okay, cool. So, we're going to be looking at deep learning as non-parametric statistical methodology. It's a beautiful blackboard. All right, so what's deep learning? These are families of nonlinearly parametrized functions trained with simple gradient methods. By now it's really a well-established methodology. Things have been scaled up hugely using kind of parallel and distributed computing, enormous data sets, and it's been extraordinarily successful for prediction problems. Had a huge impact. I mean, I'm sure you've all seen in areas like computer vision and natural language processing, speech processing, it's really been field changing. So as a statistical methodology, amazingly successful. On the other hand, on the theory side, viewing it as a statistical methodology, there are lots of aspects of this approach that are really surprising, really mysterious in some ways. So, we're going to look at a few of those really in quite simple settings. So, maybe somewhat far from practice, but cases where we can analyze things and understand, the differences between the principles that seem to be behind this methodology versus what we're familiar with in non-parametric statistics. Okay, so we're going to be working with probabilistic formulations of prediction problems. So we have, there's an input space. Let's say we'll use the notation x here, curly x. There's an output space y, and we're thinking about a probability distribution on this product space. And you can think of these as, images and labels associated with those images, or maybe these are sequences of tokens, sequences of words, and this is the next word, many different ways of thinking of these as prediction problems where we want to predict a y from an x. We're going to formulate it just in this quite general way, and our aim is to come up with a prediction rule, so a mapping from x to y, I guess potentially to another space, so that the loss of our prediction rule, we'll write it as L f hat here, is which is the expectation of the loss incurred when we make a prediction. I'm actually going to keep my notation consistent, so let's use a lowercase x here. The loss incurred when we make a prediction on the covariates x with our prediction rule f, and the actual outcome is y. This is the loss, so think of this as a non-negative function from the range of f times y to the non-negative reals. We're interested in the risk or expectation of that loss being nice and small. Okay, so this is kind of the general problem that we study, and the expectation is over. We have some some distribution on the product space here. Hello, I'm sorry. Is it a? In the loss function, is it f hat? Is it f hat? It is f hat. I'm sorry, I couldn't hear the hat. Yeah, absolutely. Thank you. Good. And do pipe up if I make mistakes, or if you have any questions, if things are unclear. Okay, so deep learning is concerned with prediction rules here that come from rich. They're parameterized function classes, but the parameter space is typically really huge. All right, so we're considering a function. We'll write it as mapping from. Let's think of our inputs as always in RD. I'll write this as a parameter space. It's also going to be some Euclidean space, but very high dimensions, and mapping to some output space. Again, Euclidean space. I'll write this as D capital L, and we'll see what the capital L means here. And these things are compositions of functions. So compositions of kind of parameterized computations that occur in layers. So we'll write f of x theta as an example is some possibly nonlinear transformation at the elf layer of some parameterized function. I'm going to write it as linearly parameterized because I'm allowing myself a lot of freedom with these nonlinearities. And this itself is a function of another non-linearly parameterized class of functions, blah, blah, blah. So think of it as, we have our vector valued input x. We take a parameterized linear transformation of that. So this W1 is a matrix, x is, so let me write out some dimensions here. So theta is kind of all of the W's together, right, where each one with, in layer L, the parameters associated, I'm writing them as W's. This is kind of a nod to the weights terminology that people in deep learning use. And WL is a matrix in our DL by DL minus 1. So we map from our input vector space to some other vector space in a parameterized way. Then there's some nonlinearity that maps from that vector space to another vector space. And this might, for instance, be ReLUs. So it may be that we're thinking about a component-wise nonlinearity. So sigma of a vector v has component I equal to the max of 0 and vi. Right? This is called a ReLU nonlinearity. These are common. We may have sigmoidal things where this is so again applied component-wise. Maybe this is I'll write it as 1 over 1 plus e to the minus vi. And all kinds of nonlinearities that get used in practice, mapping from a vector space to another vector space, and then we're composing those things, right? Again, parameterized class of things that are linearly parameterized, followed by nonlinearities and so on. And you can represent a rich family of kind of the kinds of computations, parameterized computations that people use in practice in this sort of a way. I should say that these architectural choices, so one thing about, we're always talking about a set of parameters that lies in some finite dimensional space. The way to view it is it's a high dimensional space. Although this looks parametric, we really should be thinking of it as non-parametric. There's nothing about this that is close to the notion of a statistical model, in the sense that we're not choosing the computation blocks or the way things are parameterized, the nonlinearities, any of those things. Even the scale, the number of parameters that are used in these different computation layers, is something that's chosen by trial and error and not reflecting a specific model for any process that generates the data. All right. I mean, there are kind of generic choices that you can think about convolutional transformations if you're working with image data or data of that sort, where somehow this linear transformation involves something that reuses parameters, is applying a kernel across an input space, for instance. For language data, there are attention blocks that are used, a particular way of looking at relationships between different components of the input here. So I guess at that level, the computation blocks might reflect the type of data, but it's really, really very far from a model that's specific to the or intended to model the process of generating the data. Okay. Let's see. The other kind of terminology. So I guess instead of thinking about the risk for a general prediction rule of this sort, we're really going to be talking about in each case some parameterized family, some f of that sort. So the class of functions that we can compute as we vary theta across some space. And so we'll write instead, we have our, we can write our risk as a function of the parameter vector, right? So we'll write this, and I'll keep it on this board, as the expectation of the loss of f of x theta when the outcome is y for that particular function with the value of theta. We work with training data. That is a bunch of these x-y pairs. We always have n here is our sample size. I'm going to write these as, I'll write it as just in x by y. But we're essentially always working with elements of a Euclidean space. These are drawn IID from the distribution P on the product space. And we'd like to use the data to choose a value of theta that gives us a small risk. And the kind of heuristic approach to doing that typically involves simple first order gradient methods to minimize an empirical risk, which we write as L hat of theta, which is this random variable, and it's just the expectation under the empirical distribution of the loss incurred on our sample. Okay, so this is a very general problem, a family of kind of really very simple-minded approaches, but it opens up a lot of this is nothing. It opens up a lot of interesting questions as we'll see. So conventionally, when we're faced with a prediction problem of this sort, we're used to these kind of trading off the various issues involved. So let me write out, at a high level, the kinds of things that we're concerned with are the sort of representational power of our in this case parameterized family. So here, we'd like to know that the best we can do with our class is pretty good. So we'd like this to be nice and small. We might think about pursuing the infimum over measurable functions of L of f, right? And how close can we get to that, and what do we need to do in terms of the choice? This is, of course, totally concerned with the choice of our parameterized class, right? So we want it to be nice and rich. there's a let's say computational question which is, with a limited amount of computation, we want to choose a suitable theta hat, right? And maybe we'll be using some sort of a heuristic method based on minimizing this empirical risk. The point here, the reason it's an issue is this involves a bunch of computation, right? And we'd want to make sure that this is something a problem we can solve efficiently. And then, of course, there's the statistical question, which is ensuring that L of theta hat is close to the best we could hope for, the infimum over this class of the loss. So at a high level, this is the way we're used to thinking about the trade-offs in solving a prediction problem of this or any kind. And let's say a little bit about again, just at a high level, a little bit about the kind of classical approaches there. I mean, on the approximation side, we're used to dealing with, rich non-parametric classes. On the optimization side, we're used to having nice convex optimization problems to solve, or things for which we can come up with guarantees about, how well, for instance, if we work with this empirical risk criterion, how well we can approach the optimum there and how much computation that involves. On the estimation side, we're interested, the typical approach is to think about this L theta hat, this random variable, by how much it exceeds what we're chasing. And we think about splitting that up into a bunch of different pieces. So let's go through and write that out, right? We might compare this to the empirical value for our theta hat. We might compare the empirical value to the empirical value for some other, theta in our space capital theta. We might compare that to the true risk for that theta star, and then good to have a nice long blackboard. Right, so I've just added and subtracted a bunch of things here. Okay, so this is just choosing a suitable comparator, and if the infimum exists, great, then that's a good theta star. Okay, if this is maybe at infinity or something, then let's pick a decent comparator where that's nice and small. This term is an expectation of the loss incurred by this parameter versus an expectation of the empirical distribution, a sample average. All right, so this is just a law of large numbers that we might hope to have this nice and well controlled as long as our sample is large. Right, we just have a single function, the one corresponding to f with the parameters theta star. There's nothing deep going on there. This is our optimization problem, right? We want to use, we're aiming to minimize the empirical risk. So pick a theta hat that has a nice small value here, something that competes with anything in the set theta. In particular, it's going to do better than theta star. So this quantity is going to be non-negative. Yeah, and then this is the more interesting one, and there is a whole host of ways we might consider comparing how the risk and the empirical risk for theta hat compare. So this is interesting because theta hat was chosen using the data, right? So it's a biased estimate. And we might do something crude. I'm not going to go in any detail in this direction, but we might, for instance, say, well, we're choosing theta hat from the big set theta. This thing is certainly no more than the supremum over everything in theta of L theta hat minus L hat theta hat, and and then work in terms of that sort of quantity. If we're working with the full family capital theta, and we've got a family that's rich enough that we get a nice small approximation error without a whole lot of information about what the underlying relationship between x's and y's is, then that's a big ask for this to be uniformly small, right? So typically we would have a very rich class, but we would define some sort of complexity. Yeah, question. Yeah, so we're considering, think of this as a supremum over our class of functions. Every one of those functions is parameterized by a theta in this family. Oh, thank you. Again, appreciate it. Thanks. Good. Missing hats, extra hats. Any other questions? Yeah.
Sorry, can you please recall how you use theta star?
Theta star is just some element of capital theta that's a comparator for which this difference is small. So it may be that the infimum is achieved. I guess I'm just being a little fussy here, right? It may be that the infimum is achieved. Choose theta star as the one that achieves the infimum, the best in the class.
So we don't necessarily know how to choose theta star.
Oh, theta star is just for the sake of analysis, right? Nobody's calculating theta star using data or anything. This is just a comparator that we're using to argue with a theta hat that we choose based on data. We're going to get close to the best we could do given the constraints of the class that we're using. Yeah. Any other questions? Okay. So if we're, classically we would think about having a very rich class so that, we can handle many, we can be very relaxed about the kinds of XY relationships that we're wanting to model, but we consider a complexity hierarchy. So we define. So this is the way we approach the key issues. The approximation one, we think about having a very rich class of functions. For the estimation one, we're going to have to restrict the complexity of our functions. So, for instance, we might define a complexity. I'll say, as an example of an approach, we might define a complexity hierarchy. Which involves, writing. I'll stick to the parameter set here rather than thinking more generally about function classes. But we might think about writing our parameters as a union over sets of different complexity, parameterized by this. I'll say theta. And maybe this is. This involves bounds on norms, of some kind of these parameters. The point here is we've got a kind of increasing bunch of subsets of increasing complexity, and for any one of these subsets, we can say something about their statistical properties. This sort of statistical property, for instance, that across this bounded complexity class, we can keep control of keep control of these uniform deviations between sample averages and expectations. Yeah, question. I'm sorry, could you say that again?
What do you mean by the complexity of the subset?
Yeah, I'm being very vague. You could, for instance, so it turns out that if the loss random variables over there that we're averaging have nice tail behavior, maybe they're sub-Gaussian. We heard about sub-Gaussians in the last lecture. Yeah. So if these things are sub-Gaussian, then it turns out you can characterize this supremum in terms of the Rademacher averages of the family of loss functions. So there's a very, very specific notion of the complexity of a set of functions. The relevant set of functions is, this family of functions from x, y to the reals that indexed by theta in some subset, right? And the notion of complexity that arises when you consider something like this, when the tails of those random variables are nicely behaved, ends up being, it's kind of within a constant factor. It's the Rademacher averages of that family. What is that? It's like an empirical process indexed by the theta in this case that gives you, some notion of, it's a non-negative quantity that gives you some notion of the richness of the class and characterizes, what this thing looks like as a function of sample size n. And we might, so when we're talking about parameterized families, we might do a kind of count of the number of parameters, and you can get bounds on Rademacher complexity. In that case, we might keep control of the scale of those parameters, and this gives you another way to measure to control the relevant quantity here. If we're looking more generally at smoothness classes or something, maybe we're working with functions in a reproducing kernel Hilbert space. Again, the kind of right thing once you've taken the leap of this crude inequality, the right thing ends up being the norm in that RKHS. That's the right way to build this complexity hierarchy. So, there are a whole lot of these results of that form that are known. I'm being kind of vague and hand-wavy here because this is the straw man that I'm putting up there as this is the beautiful theory that we have, and deep learning doesn't fit in. It's really very different. So I apologize. I'm not being particularly thorough in this kind of overview talk. But happy to take any more questions if it's still confusing. All right, so the classical approach is to define this sort of complexity hierarchy to come up with, to make sure we keep control of, the relevant term for the estimation part of the story, and that might mean, for instance, that we trade off the fit to the data with some notion of the size of the parameters. So we might have some sort of a regularization term that appears in our criterion. So rather than just directly over the full class minimizing the empirical risk, we might have some sort of trade-off between empirical risk and whatever appears here as the index of the complexity hierarchy, which might be like the coefficient of a regularization term, kind of speaking vaguely. So we're used to doing that sort of balance of complexity with the fit to the data to address the kind of estimation issue. And for the optimization issue, we're used to having nice convex loss functions, right? So in particular, the map for every fixed sequence of XY pairs, the map from the prediction here to the loss is a convex function, and this function is linearly parametrized in terms of the theta. So as a function of theta, this thing is a convex combination of convex functions. It's itself convex in theta. That's beautiful because then, we know that we can we can have a very good handle on the computational complexity of finding a near optimum to a convex function. Okay, so that's a nice tractable family to deal with, where we can address this optimization issue. So in deep learning, it seems that these trade-offs are addressed in rather different ways. I guess in particular the optimization and estimation parts of the story, seem to be quite different with deep learning methodology. So, maybe just to again give the kind of hand-wavy overview. Let me erase a part of this. So we certainly don't have a nice convex optimization problem to solve when we consider these compositions of parameterized functions. This is a really ugly sort of parameterization. That means that even if our loss is convex, which it typically is, as a function of the parameters, we have something that's really very far from convex. And you can prove various sorts of hardness results. If you constrain the class of functions that you're working with, these sort of think about neural net sort of parameterized classes of this sort. Once you get to 2 layers of parameters, so get beyond a linear parameterization, you can prove strong negative results about the computational complexity of minimizing a function like this. But what turns out in practice is that the optimization part seems to become, I'll say becomes, but this is just an empirical observation. Seems to become easier with overparameterization. So as you consider richer and richer parameterized families, come up with a kind of, they call it architecture, so one of these choices of a parameterized function class that has more and more parameters, the optimization problem that you want to solve becomes easier and easier. It's of course still an ugly non-convex optimization, but these simple gradient methods seem to reliably find very good solutions. And I'll say a little bit more about that. If the number of parameters becomes very large compared to the sample size, then maybe that's not so surprising, right? That there's this whole sort of manifold of solutions then in parameter space where you can achieve whatever loss you want to achieve because you've blown things up to have such a rich class that actually you can drive that loss to 0. Let's suppose our losses are, have in your head the squared difference between these two, right? So quadratic loss. So that makes the optimization problem much easier if you blow up the parameter space. But that sounds like a bizarre thing to do from a statistical perspective, right? Because you're just finding a solution if these in let's say in a regression problem, if the y's are very noisy, the best prediction of y with squared loss is the conditional expectation of y given x. And if the y's have some additional noise on top of that, right, then driving this loss to 0 is a crazy thing to do. You're just fitting to the noise in that case. So okay, maybe this isn't so surprising from that perspective once you get to a sort of sufficient level of overparameterization, but it seems like a foolish thing to do from the perspective of the estimation question, because then your classes become too rich to have properties like uniform convergence being true, right? If your dimension of your parameter space is large compared to the sample size, you can't hope to have this supremum being anything non-trivial. Okay, so that's one feature that the practitioners have observed. Another behavior is that you certainly do get overfitting. So you can reliably get the loss driven down to a small value, even in cases where there's noise in the Y's because it's an experiment, a controlled setting. You add noise to the Y's. You know that it's noisy data. You can still get this loss down to zero with kind of practical choices of the methodology that practitioners use. So so you certainly are fitting better than you should expect. Let's say in a least squares setting, getting that loss down to zero is certainly overfitting when there's noise. On the other hand, that overfitting ends up being rather benign. You can have a near perfect fit to the data and still have good predictive accuracy with these models, which is really quite a striking thing from the perspective of this sort of theory. I mean, you're really very far from having uniform convergence in that case, right? We're driving this quantity down to zero and getting this near optimal, but in a noisy setting, of course, near optimal is a constant away from zero. So, sample size growing, we're very far from having this thing go to zero. This is a striking phenomenon that we see in these models. Okay, and then one thing to think about here. We know from classical theory, this is a loose inequality. Okay, so certainly we might expect for instance, in a least squares problem. We know, let's think just about linear regression, very classical setting. We know that this quantity decreases like 1 over n, right? Like let's say d over n if we're in a dimension d space, right? So as long as we keep that dimension fixed and increase the sample size, we're getting a nice 1 over n sort of decrease of this, the magnitude of these sort of deviations between the least square solution's risk and its empirical risk. Okay. Actually, I'm saying, forget this line for a moment. In that example of linear regression, I don't want to open up a can of worms. In that setting of linear regression, we know that we can approach the optimum at a 1 over n rate. On the other hand, this kind of quantity outside of completely trivial cases is never better than a 1 over square root of n, right? So the supremum over the class is really a crude way of controlling the behavior. On the other hand, we also know that if you really are getting a perfect fit to the data, then then we shouldn't expect good predictive accuracy, right? There are lower bounds that tell us that for some of those solutions we should have very, very poor values of the risk. The risk should be far from optimal. But the thing is that there's a large set, if we're in an over-parameterized setting, there's a large set of parameters for which we can get the empirical risk to zero. All right, so everything's smooth. This is like maybe a manifold of parameter values where the risk is zero. We know from classical theory there are some points on that manifold that are terrible. You know, they all have empirical risk 0, but some of them have very large risk. On the other hand, gradient methods are not going to just any point on that manifold, right? They're favoring particular points. That's just the nature of the algorithmic approach that's used. So, you know, it seems that we should be attributing this behavior to the choices that those, the algorithmic choices that drive us to particular theta hats in that big set of empirical risk minimizing ones. So, you know, one important issue there is this notion, this notion of the what's called implicit regularization, which is you know, terminology that has been widely used to describe the properties of the solutions that the algorithmic approach to minimizing the empirical risk impose on that they impose. So what kinds of empirical risk minimizers do let's say these you know, gradient descent or gradient flow or any of these simple first order gradient methods, what kind of solutions do they find? So that's one, you know, these two issues are going to be the main focus of my lectures. We'll be looking at first at what are the properties of solutions that gradient methods find in a variety of settings, and we'll see that depends, you know, on a whole range of different aspects. It certainly depends on the loss function. It depends on the way things are parameterized. It depends on algorithmic choices. You know, the kinds of algorithms that are used, gradient algorithms that are used to minimize this quantity. So, you know, we'll explore some results of this form, and we'll see that, you know, this is called implicit regularization. You know, I think the terminology became popular because the sorts of properties are related to things that we're familiar with from controlling complexity in more standard statistical settings. And then the benign overfitting direction, you know, is really in simple settings trying to understand how we can have a perfect fit to noisy data and still get good prediction accuracy. You know, having a perfect fit, I think, is a kind of interesting edge case, interesting limit case, and certainly the what happens in practice might not be at the L hat equals 0 sort of limit, but you know, this is I think really very informative. Okay, and the other aspect that that I would like to explore, but I'm not sure that we'll get to in these lectures. It's another aspect of the interplay between optimization and estimation. You know, there are aspects that are just optimization specific and aspects where the optimization choices have an impact on the statistical properties. But this is about, let's say, large step sizes, large step size gradient methods. So in optimization theory, we think about, you know, in working with gradient methods, we think about the kind of choosing gradient descent over as a kind of computational implementation of a differential equation like gradient flow. You know, and maybe there are more sophisticated second order methods. There are accelerated gradient methods like Nesterov's approach, which can be viewed as a time discretization of a second order differential equation, you know, as opposed to the first order gradient flow. So, this is the kind of perspective that optimization theory has mostly taken, which is just that we're really considering something that is a continuous time process, and we're discretizing it because we have to compute it. So, turns out in practice, that's far from the situation. The practitioners choose step sizes that are really very large, much too large to be considered a time discretization of a nice differential equation. So certainly you choose a step size too large, above 2 over the largest eigenvalue of the Hessian in a setting like this. We're working with gradient method, and you'll diverge. That's fine. In the quadratic case, the intuition is really not helpful because there you're either too large or you're stable and you converge. But it turns out if you're not quadratic, then there's this whole range in between. You can have a large step size where a step size too large where you diverge and nobody's going to use that in practice, obviously. You can have a step size that's nice and small where you converge monotonically, and that's a very good approximation to a differential equation. But in between, there's this regime where, oscillations happen, things descend nicely and oscillate and descend nicely. That's the regime where, that the practitioners have settled on, and it's actually quite, clearly far from a regime where you're approximating a differential equation, in discrete time. It turns out that there are benefits. There are, you can prove some quite significant optimization benefits, ignoring the statistical questions, optimization benefits of taking a large step size. So stepping away from that differential equation, you can do better. And in terms of statistical properties, there are also some statistical properties that you can prove that apply to the sorts of solutions you converge to with a large step size, as opposed to the ones you'll find with, let's say, a gradient flow. By choosing a solution to a differential equation when with the same, let's say, random initialization. So, at a high level, I guess, the theme of these lectures is that, when we're classically used to kind of compartmentalizing the optimization part, that's just something that someone else is going to worry about, and as a statistician, I don't care. They'll just give me a nice, efficient way of finding a good solution to my optimization problem, and then I can be concerned about the estimation part, and maybe I'll impose some nice convex regularization on my nice linearly parametrized convex minimization problem to deal with this. So we can kind of compartmentalize things and think about them separately. In these rich, ugly parameterizations that arise in deep learning, it turns out that these issues get very much intertwined, and the kinds of approaches that are taken to the optimization have a big impact on statistical properties, and it's that interplay that we're really addressing here. Okay, so that's the kind of overview of where we're going in these lectures. So it might be a good point to pause. I know I've been very hand-wavy and vague. We'll get into some more details shortly. All right, good. So let's see. We are 50 minutes in. We have until 12:20. We have another 40 minutes, right? 12:20. Okay. Great. So let's get started with some of these questions about. We're actually going to start with implicit regularization. The second part of the lecture series will be on benign overfitting, and third part, if we get a chance, will be on large step size. And we'll finish with, in the last lecture, I want to give a bit of a future directions kind of spiel, right? So we're looking at these kinds of phenomena in really very simple settings where we can understand them. So you know, there's a lot that's still open in this area. Okay. Thanks. So let's get started with implicit regularization. I want to start by, you know, defining some of these gradient methods that I've spoken vaguely about, and we'll see. We'll see probably in this time just one example, looking at a linear regression problem, an over-parameterized linear regression problem, and see what phenomenon arises there. And we're going to do a little bit of review. Probably this will be next lecture, but we'll do a little bit of a review of constrained optimization. So you know, you're going to be faced with some optimization theory. You know, it's kind of inevitable here. It's a mingling of those two areas, right? The optimization and the statistical side. You know, maybe a little bit off the traditional Saint-Flour sort of set of tools. But I hope you find it interesting. Okay, so let's start with going through some gradient methods. You know, I will be dealing with the losses that we'll be concerned with in all cases, even when we get to the sort of rich, ugly parameterizations, we're dealing with nice convex loss functions. So, you know, our L might be, for example, L, we might work with, so, you know, we're actually going to be a little explicit about predictions and outcomes. You know, these are the random variables. This is the range of our prediction function f, and they may be different. In the case of linear regression, they're presumably the same. Let's suppose we're just predicting a scalar, so these both are real numbers. So you know, maybe we'll think about this as just y minus y hat squared. We might consider the logistic loss in a classification setting, and this is the one that is really much more common in deep learning. I think if you're talking about classifying images, if you're talking about predicting the next word in a document, which is the basis for, you know, these amazingly smart LLMs that can, you know, do all these rich things. The loss, at least in the pre-training part, the loss that's minimized there is just the log of the predicted probability for a discrete probability model, right? So let's write that out in the binary case. You know, so here this is where the prediction space is the same as the outcome space is the reals. In logistic regression with the two-class case, we might have y hat y. So here, the prediction space is the reals. The outcome space is, let's just say two-class, so plus or minus one. And our logistic loss here is the log of 1 plus e to the minus y hat times y. Let's write it like that. So you know this in logistic regression, our y hat is a linear function of our covariates. That linear function is in this logit space, right? So we're thinking about that as being. So we could write this, okay, that's equal to the negative log of, I can think of it as p hat for the prediction y hat. This corresponds to a predicted probability of one of these plus or minus 1 outcomes, right? And our loss function is the negative log of that predicted probability, right? So we want to make our predicted probability kind of as large as possible, the predicted probability of the correct outcome, and you know, in that case we're interpreting this real valued beast as, you know, a transformed version of the predicted probability of a 1 with this logistic, right? So the predicted probability of an outcome of 1 when our let's say in logistic regression, when our linear function takes value y hat, is e to the y hat over 1 plus e to the y hat, right? So it's this sigmoid. Okay, so there's a probability model here that's sort of hidden in the y hat, and we're interested in this negative log of our predicted probability is our loss function. You know, plug those things together, we get the loss incurred when the outcome is this plus or minus 1 value, and our prediction our prediction is this real value, and our outcome is that plus or minus 1, is this convex function of the prediction y hat, right? And this convex function, you know, goes to 0 exponentially if we've got the right sign, right? If y hat has the correct sign, we've got a nice exponential tail, and on the other side it's Lipschitz, you know. So we'll be playing with these properties a lot in what follows. Yeah.
So you mean the capital Y and capital Y hat is real valued random variable?
Here.
Capital, yeah.
The curly y hat is the set of real numbers. Y hat is an element of that set. This is supposed to be a lowercase. Maybe it's my typography that's not very good. Yeah, this is the prediction that corresponds to, you know, f of x theta, for instance, and this is the outcome that we see in this binary classification case. We have covariates x and outcomes that are in this set y of plus or minus 1, and our predictions are real valued, and we impose a loss, a logistic loss here that corresponds to, you know, this prediction is actually an ingredient in our probability model for the outcome y as a function of x, and the loss really is the negative log of the probability we predicted for the outcome we actually saw.
So the p hat has the 2 arguments.
Yeah, so this is the probability model that corresponds to, you know, using this loss. And I'm never going to use these predictive models again. I'm just, you know, just wanting to justify the logistic loss that we'll be using with real valued predictions in a classification setting.
Okay.
Yeah? Any other questions? Okay, so, you know, these are 2 key examples we're gonna be working with. A couple more definitions, you know, really very simple. Okay to erase this? Yeah. Couple more examples. A couple more definitions we'll be working with. So, you know, we're dealing with computational approaches that involve gradient methods. A gradient flow is a continuous time gradient approach. It's just defined by this differential equation. So let me just first say we're working with an empirical risk. We'll write it as a function from R, and I better get I'll call it RD. So this is our parameter space. We have parameters that lie in RD, and we're wanting to minimize this empirical risk. We have an initialization that may well be a random variable. Whatever, it's theta 0, that's some element of RD. We have a gradient flow on blah, blah, blah with initialization theta 0 is a function of time that satisfies this differential equation that the time derivative of theta is the negative grad L hat of theta t. All right, so this is gradient flow. We can think of gradient descent. The usual way to view gradient descent is as a time discretization. Again, I'll be a little careful with initialization. Theta 0. Again, this is on L hat with initialization theta 0. And step size eta is a first order difference equation. Gradient descent blah, 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 is the sequence theta t plus 1 is theta t minus eta times grad L hat theta t. Okay, so we're just doing a straight, what's this called, Euler discretization of our differential equation to come up with this discrete, with this difference equation. And I guess there are variants. So, in practice, if L hat is an average across a very large data set, then computing this gradient to take a step, is a very big computational effort. And so, in fact, you don't typically see that. You'll see people do variants of stochastic gradient descent. Which is, again, I'm going to say on L hat with initialization theta 0, step size eta, blah, blah, blah. And now we're going to take a random step. So instead of computing the gradient of L hat, if L hat is an average, if L hat has exactly this form, so for L hat having this form, we're going to take a step in an unbiased estimate of the gradient of this thing, and our unbiased estimate is computing just a gradient of one term in that average. Yeah, so this is theta t minus eta times grad little l here, and I'll write it as f of x. So now this is an IT, theta t yit. Okay, where with and I guess there are a bunch of variations on how you can choose things here, but you know we might choose IT. Let's say independent and uniform on 1 to n. And you know, other choices are possible. You know, there is mini-batch stochastic gradient descent where you take an average over a random subset of the training data, right? Rather than picking a random single example. Okay. All right, so let's talk about a very easy case, gradient descent for linear regression in an overparameterized setting. So we're working with this loss. And considering, you know, actually considering all of these, but let's say gradient descent. All right, so linear regression. It's nice and easy to analyze because we have, you know, linearly parameterized f, and of course a nice convex loss. So our empirical risk here, L hat of theta. So I guess maybe I should write out linear regression. So we're going to work with, you know, f of x is just inner product between x and theta, and I'll use this matrix vector notation for everything. You know, there's in many cases we'll be working with things that can be from a Hilbert space. I'll keep on using this notation even then, but let's think about you know, just a finite dimensional case here. So our loss is the average of these losses, so 1 over 2n of xi transpose theta minus yi. This is all, you know, the example we hit our undergrads over the head with so many times. So, okay, so we have a data matrix here. We'll write it this way. X is our vectors of covariates as row vectors, x1 to xn. Right, so it's an n by d matrix. I think I called it d. And y here, a little hard to, maybe I'll put a vector sign over it, and I'm sure I'll forget it, so I apologize in advance. This is the vector of outcome, so this is our training data here with the covariate outcome pairs appearing in the data, the X matrix and the Y. And you know, I'm going to dwell on this a bit because you know, we'll see when we get to the benign overfitting setting, you know, this kind of quantity arises in the linear regression case again. The properties of this matrix are really important there. So this random matrix is an n by d matrix. Okay, so the cases we're interested in are the overparameterized ones where d is large. So it's a fat matrix. Right, that's the example to have, the typical case to have in your head, where d is big compared to n. So then, you know, when we minimize the empirical risk, we get a set of minimizers that's going to be an affine subspace in RD, right? Because we've only seen n examples and we're in this d-dimensional space. Okay, so gradient descent is converging to a specific element of that subspace. So let's write it out, and I'm kind of going to spell things out in this lecture. I do want to make sure we have some of the intuition for what goes on in an over-parameterized setting. So let's write it as, let's call it a theorem. It's a simple observation that, let's not be concerned with the optimization side of things. So let's say if gradient descent converges, let's say to theta hat, then theta hat is the minimizer. Theta hat solves this optimization problem. It's the closest point to theta 0 that satisfies the normal equations. X transpose x theta is x transpose y. Okay, so and in particular, if we start off, okay, so for theta 0 equals 0, this is theta hat is arg min. Is the smallest norm. I guess I should say for theta hat is 0 and x has rank n. Is the smallest norm that interpolates the data exactly. Okay, so when d is large, think of our x having a density. This is what we'll see, and this means that for every x-y pair we have, our prediction on xi is equal to yi, and I forgot the distinction between the training data, the training y's and the random outcome. Okay, so this is a nice simple result, and I want to it's a very obvious thing. I'm going to kind of belabor the proof, give you a sort of linear algebraic proof, because I want to get the feel for the role played by the scaled sample covariance matrix in this setting, and we'll actually see a second simple proof in terms of using tools from optimization theory, from constrained the theory of constrained optimization. So we'll do that. Okay, so it's really very simple to see why this is true. If we work out the gradient of the empirical risk, we can write that down as just L hat of theta. This thing is just 1 over n x transpose x theta minus y. So when we're working with gradient descent, or indeed gradient flow, or even the stochastic version, we're restricted. Our updates are all in directions that come from here. So we're restricted to the row space of x, all right, because we have an x transpose appearing. We can only converge to a stationary point of the empirical risk. you know, stationary point means we're solving the normal equations. That this is the expression for a stationary point. All right, x transpose x theta equals x transpose y. We can think about decomposing theta into you know, the row space of x. Let's say so this range, this linear operator, the range of that linear operator is R, the row space of x. So we can think about, and we're making our updates only in the row space. So all we can do is fix what goes wrong in the row space of x by taking our steps in that subspace. So let's decompose our parameters as they evolve into the row space and the complement of that row space, the kernel of the scaled sample covariance matrix. So we can write. Okay, so I guess the other thing is because x transpose x has row and column space R. There's going to be a unique element of R that satisfies this optimality condition, the stationarity condition. All right, and so a unique element of R, let's call that theta R star. In R. And so we can write, you know, anything that satisfies the stationarity condition, we can decompose into its component in the R space and the orthogonal component. So, so things that satisfy this stationarity condition are just of the form theta R star, the unique element of R that satisfies this condition, plus, you know, whatever we can do in that orthogonal complement to R, which is this, the full orthogonal subspace, that's the kernel of x transpose x. Okay, which is, you know, however we write this, it's the orthogonal complement to R. Okay, and then alternatively, if we think about this problem, the minimizers, this problem, the minimizers of the distance to theta 0 such that we're satisfying the stationarity condition, you know, we can split this thing, you know, versus, let's write theta minus theta 0 squared is what we see in the R subspace together with what we see in the, so let's write it out directly. Theta hat, this solution to the min over theta of this thing such that x transpose x is x transpose y. We can write this as what happens in the R subspace. How am I going to write that? Maybe I'll write this theta 0 R plus the other bit, and I call that R complement. Such that this happens. But you know, it's clear that I missed a theta here. Anything that goes on outside the, you know, the kernel of this has no impact. So this is just such that theta R is theta R star. and this term we can have no impact on, right? So you know, this term only hurts, I guess I want to say, right? So getting theta r right, we should make this term 0, which means leave theta. The solution here should be theta 0, whatever it was at the beginning, and then this thing is whatever theta r star gives us. So this is exactly you know, theta r star minus theta 0 r star squared. Okay, so the minimizer, so I guess I should have written argmin is the same thing, is just theta r star plus the orthogonal bit. All right, so it's clear that we're getting a we're only working in that subspace that matters, the row space of X. What I want to do next is see that the same thing arises when we consider that this is a sort of distinct immediate consequence of you know, a kind of quite general result from optimization theory, result about this constrained optimization problem, right? Which is this constrained optimization problem, which is, you know, minimizing this quantity subject to our equality constraint here that we satisfy the stationarity condition. So we're going to think about you know, and I guess this is immediate. If we start at 0, the theta 0 in the orthogonal subspace is not of any interest. So so we have a few minutes. So maybe we could make a start on some of the constrained optimization background that we're going to use in the second lecture. Yeah, question. Yeah, I'm just writing theta 0 as the initialization. It may be random. It may be deterministic. Yeah. So you know, in practice, people use what's typical is a small random initialization. So in this setting where things are convex, you know, that doesn't make much sense, and a 0 initialization is great. But for the sort of parameterized classes that I described at the beginning, it turns out 0 often ends up being a nasty saddle point. And so it's not uncommon to choose a non-zero initialization, but make sure the initialization is small. Okay, so you know, for gradient methods, I mean, there's a whole other direction that people have pursued that I'm not a big fan of. It turns out if you have a large initialization for one of these parameterized families and a small step size, then a linear approximation around the initialization ends up being a good approximation in the overparameterized setting, ends up being a good approximation throughout the training process. So you can actually view the whole thing as, you know, a linear class of functions with a convex loss. But that's really unrealistic. You know, it's a setting where you know, you're really very close to the kind of things where we're analyzing as this sort of these simple first special cases, and you never stray away from those. In particular, you're not really exploiting the nonlinearity of the class, right? You're working with effectively a random set of features, and linearly combining those. So yeah, you know, in practice, the initialization is small, and this is, you know, a reason for that. but it can't be 0 because there's this kind of ugly saddle point at 0 that is problematic. Yeah. I think that's presumably the real reason for a random initialization in these kinds of problems. And I guess so there are cases where you can say something about the sort of mass of initial points that have a particular property, and what's usually exploited there is the symmetry of the initialization, and so that's not so important. It might be Gaussian, it might be on a sphere, but it's the symmetry that typically is kind of the crucial thing. But yeah, in this setting, let's think of theta 0 as 0. Yeah. Any other questions? All right, so we have 6 minutes, so I'm not sure that there's a. Well, let's at least do an easy statement of what goes on in unconstrained optimization, because we want to look at the constrained optimization setting, because next time, we want to study optimization problems like this one. And properties of solutions of those constrained optimization problems. So we're going to get to meeting the Kurush-Kuhn-Tucker conditions and things of that flavor. All right, so all right, well, let's put this up at least. And okay, so this has the flavor of an aside, and it'll be 5 minutes now and a part of the next lecture, and it's really sort of some optimization background that we'll be using. Yeah, so the setting is we're optimizing. We're minimizing. So consider minimizing f, let's say on RD. It's real valued. We're considering a set, I guess I should call this a curly X. That's a subset of RD. Okay, so I'll write this as a theorem. If f is differentiable at 0 at x star, I'm sorry, in this set. Okay, sorry. Let's think about first of all the case where x is all of RD. Then this is kind of a simple observation. X star is a local minimum of f in RD, implies it has gradient 0. So local minimum means, for all x, within epsilon of x star, f of x is at least as big. Yeah? And secondly, if f is convex, then we have an if and only if. F is convex and gradient is 0. We have this nice situation. X star is a global minimum. Right, so for all x, f of x is at least as big as f of x star. Okay, so in the constrained case, we end up with, we have to worry about what happens in those directions that would decrease f but would take us out of x. Okay, so this is more interesting. So for that, we need a few definitions. We need to say, I've run out of time. Okay, so we need to think about tangent directions to the set X. We need to think about the tangent cone to X at a point, which is sort of the set of tangent directions. And then we need to think about the set of directions that don't help when we're moving downhill because they would take us out of the set. So we need to think about the polar of the tangent cone. All right, so this is the set of kind of things that have a non-positive inner product with points in the tangent cone. And then our condition, this trivial, derivative is 0 at a local minimum becomes, the downhill direction, the negative derivative, is an element of the polar of the tangent cone. That's the kind of corresponding condition here, the general condition, and for the beautiful convex case, there's an if and only if, and we have that if the downhill direction is in the polar of the tangent cone, then we've got a global minimum in the convex case. Convex f and x is convex. Right, so there's a generalization like that, but that condition of the polar of the tangent cone, this is a hard thing to work with in general, and we'll look at special cases and how we deal with those that end up being, things of this sort where these are the kinds of constraints, the kinds of X sets that we'll be fighting. So, all right, so I'll stop there. Are there any questions before we break for lunch? Yeah.
May I ask you introduced row space in the discussion, consider row.
The null space of the X transpose X, yes.
Why you introduce row space? So,
Row space, I'm sorry.
row,
Yeah.
Why you introduce?
Yeah, because we have these. The row space is the space spanned by the data in D, right? D is very large, and we only have n points, so we've got an n-dimensional subspace where the data lies, these are the only directions in which our gradient updates can occur. So we're bouncing around in those directions and not doing anything in the orthogonal direction. When D is large, which is kind of, that's the right mental picture to have in these much more complex situations. When D is large, that's what's happening. We've got this really limited part of our parameter space where all the action is happening, and there's a big orthogonal subspace where we're not doing anything at all. Yeah, so that's an important space to keep in mind. And the linear case is, very nice, simple picture to have in your head.
Thank you very much.
Sure. Yeah.
Just a small comment. Nobody mentioned, but I'm quite sure that you would like the course to be substance-free. But is it possible to move a bit faster?
A bit faster. Yeah.
I mean, this theorem, for example.
This is true. Yeah. I really only wrote it down to contrast with the one I'm about to write down, but that will be next lecture.
Okay.
So yeah, I appreciate that. I was not thinking this was anything grand, but yeah, thank you. All right.